Good evening. So today I'm going to continue the example that has been left over from last time. And I believe we are about to begin the second iteration of phase 2, right? So we have initial tableau, of course, and the new basis set, which is 632, and the new basis inverse matrix, right? Next, we are going to start the second iteration. Number 2 of phase 2, right? And of course, the first step is to compute the simplex multiplier vector pi. So pi can be obtained by objective coefficient vector corresponds to the current basis set times the basis inverse matrix, right? And currently the basis set is 632, which means CB becomes 4, 4, 5, right? And the basis inverse matrix should be right here. Okay? And in my calculation, I have 1.125, 0.3125, and 1.5313. Okay? That's the simplest multiplier vector. And if this iteration number 2 is the final stage, for example, then this pi value should provide the dual solution, right? According to the duality theorem. Next is step number 2. Compute the reduced cost of all the non-basic variable. Currently, the non-basic variables are x1, x4, x5, x7, and x8, right? And because x9, 10, 11s are the artificial variable, and W is the phase 1 objective function. So we should eliminate all of this, right? For the efficiency of the computation. And the reduced cost for x1 variable, x4 variable, x5, x7, and x8 can be obtained by the objective coefficient which is okay, thank you. 3 and 7, 5 and 0, 0, right? Minus the simplex multiplier vector, which is these values, right? Pi vector times the coefficient matrix belongs to all these non-basic variables, right? So it should be 3, 2, 1, right?
Isn't the 3 part of the objective function?
Oh, yeah, you're right. Sorry, it should be 2, 1, 0, right? Yeah, thank you. And then next column is 1, negative 1, 3, and 0, 3, 1, and 0, negative 1, 0, 0, 0, negative 1, right? And in my calculation, the reduced cost for x1 variable is 0.438. Reduced cost for x4 variable is 1.594. The reduced cost for x5 is 2.53. And the reduced cost for x7 is 0.313. And the last one, the reduced cost for x8 variable is 1.53. Okay? And because the reduced cost for all the non-basic variables, so all non-negative, right? So the current basic solution is optimal, right? Then how do you get the objective function value? Objective function value can be obtained by objective coefficient vector corresponds to the basis, current basis, CB, times basis inverse matrix times the right-hand side values from the original table, right? And what is this? That is the pi, right? We already got it. So, what is pi? Pi is 1.125, 0.3125, 1.5313. What about the value of b? It is 10, 12, 15, right? Times 10, 12, 15. Right? And if my calculation is correct, it must be 37.9688. Okay? What about the optimal solution? Optimal solution can be obtained by beta, right? That is the basis inverse matrix times right-hand side value from the original table, right? So we have solved this problem, right? Using the revised simplex method. Okay, next, let's try to construct the corresponding dual problem. Okay? Because the primal problem is minimization problem, the dual must be maximization problem, right? And let's say the objective function value is W. Okay? And because in primal problem we have only 3 constraints besides the non-negativity restriction, which means in dual problem, in maximization problem, we must have 3 decision variables, right? And in minimization problem, we have 6 decision variables, which implies we must have 6 different constraints in the maximization problem, right? And the right-hand side values serves as objective coefficient, and the objective coefficient becomes the right-hand side values, right? And the constraint coefficient from the minimization problem, where the transpose of the constraint coefficient, the minimization problem, becomes the constraint coefficient for the maximization problem. Okay? So let's use y variable as a decision variable. So 10 y1, 12 y2, 15 y3, right? And it's going to be 2, 1, 0. Oops, I'm sorry. 2, 1, 0. This way, right? And negative 1, 0, 4. 1, 0, 4. The third column is 0, 3, 2, right? 0, 3, 2. And the x4 column is 1, negative 1, 3, right? 1, negative 1, 3. And x5 column is 0, 3, 1, right? 0, 3, 1. x6 column is 3, 2, 0. Right? And the right-hand side value becomes 3, 5, 4, 7, 5, 4, right? 3, 5, 4, 7, 5, 4. Okay, and in the minimization problem, all the decision variable is greater than or equals to 0, right? The minimization problem, all the decision variables are greater than or equal to 0, which implies the maximization problem, all the constraints should be less than or equal sign, right? And in the minimization problem, the first constraint is equal sign, right? minimization problem, the first constraint is equal sign, which means the first decision variable in the maximization problem should be unrestricted in sign, right? So y1 is unrestricted in sign. And second and the third constraint in the minimization problem is greater than equal to equal sign, right? In minimization problem, the second and the third constraints are greater than equal sign, which implies the second and the third decision variable in the maximization problem should be greater than equal to 0, right? So y2 and y3 must be greater than equal to 0, right? So this is the dual problem, okay? Then let me ask you a question. What is the optimal solution to this dual problem? Yeah, the pi values from the last iteration, right? Which is this. This means the first pi1 value. The pi1 value is the y1 value, right? And pi2 is the y2 value. Pi3 is the y3 value, okay? If you use these y1, y2, y3 values, right here, the dual objective function, then you will get the dual objective function value, right? Right away. So the dual objective function value is 10 times 1.125 plus 12 times 0.3125 plus 15 times 1.5313, which must be equal to 37.9688. Okay? Because we've learned that from the duality theorem, the simplex multiplier vector pi provides the optimal solution to the other side of the problem. Okay? Okay, so any questions about the revised simplex method and the duality? I'm sorry?
Can you apply to what we were doing to the big M?
Big M method?
Yeah.
Yeah, it's also applicable. Yeah, but you know the two-phase method does require a little bit more work, right? So I just worked on the two-phase method, but it's also basically it's the same, right? Okay. And then let's move in to the sensitivity analysis. So starting from today, for the next couple of hours, I'm going to talk about the sensitivity analysis, okay? So using the sensitivity analysis, we may answer the questions like this. How changes in the coefficient of the objective function affect the current optimal solution, or how changes in the right-hand side value of current LP affects the current optimal solution, like that. Okay? And this sensitivity analysis is very important because the values of an LP's parameters, like right-hand side values and the objective coefficient, those values may changes. Okay? And if those values changes, then a knowledge of sensitivity analysis enable us to determine from the original solution. How changes in those LP parameters change is optimal solution without solving the whole problem again. Okay? Okay, so to illustrate the basic concepts of sensitivity analysis graphically, let's reconsider the window glass example, which has been covered earlier this semester. So in this example, window glass makes two different products, doors and windows, in three different plants, you remember? And there is a different time requirements for producing these two products in each plant. And each plant has different capacity, which results in different time schedule in each plant. Okay? And the profit per door and windows are $3,000 and $5,000 and so on. And all the information has been summarized in this table. And we are required to provide a production plan which maximizes the profit of window glass, right? So to formulate the mathematical linear programming model for this problem, first of all, we must define the relevant decision variables. So you must decide how many doors and windows must be produced each week to maximize the profit. Okay? So we define two decision variables, x1 and x2, represents the number of batches of doors produced per week and the number of batches of windows produced per week, respectively, right? And for this problem, our goal is to maximize profit. So if we set G equals the total profit per week, let's say in $1,000, then our objective function would be maximize 3,000 times x1 plus 5,000 times x2, right? And we also need to determine the constraints. In plant number 1, only 4 hours are available per week, and each batch of doors produced per week uses 1 hour of production time per week in plant number 1. So this restriction can be expressed mathematically. x1 is less than or equals 4, right? Likewise, plant 2 imposes the restriction that 2x2 is less than or equals 12, right? For plant number 3, you would get 3x1 plus 2x2 is less than or equals 18, right? Because the production rate cannot be negative, it's also necessary to restrict all the decision variables, x1, x2, must be non-negative, right? So the complete math formulation would be like this. And this is the corresponding Lindo output for window glass example. And besides this result, Lindo provides additional information which can be used for sensitivity analysis. Okay? When you run Lindo, you will get small pop-up window like this, asking information for sensitivity analysis. So at this time, if you click yes, then you will get the information, something like this. Of course, you are going to learn how to use all this Lindo output for sensitivity analysis later on. Okay? Also, I'd like to let you know that after you solve the problem using Lindo, if you select Report and then Table from the pull-down menu in Lindo, then you will obtain the final table with optimal solution like this. So in this case, the first row represents the objective function row, right? So this first row is the objective function row, okay? And the last column, this one, represents the right-hand side values, okay? Which means the optimal objective function value is 36, right? And the corresponding basic variables are x1 equals 2 and x2 equals 6, okay? Okay, now let's find out where the optimal point is using the graphical method that we've learned before, okay? Okay, here, the blue colored area is the feasible region of window glass example. And in this feasible region, how many extreme points do we have? 5, right? Each corners becomes the extreme points, right? So we have 1, 2, 3, 4, 5, right? So one of these points must be optimal. Must be an optimal point, right? Now let's search for the optimal solution. To find the optimal solution, we need to graph a line on which all the points have the same z-value. That is called the isovalue line, right? To draw an isovalue line, we just need to choose any point in the feasible region and calculate the corresponding z-value, right? So just arbitrarily, we have chosen 0, 2, okay? So for the point 0, 2, the corresponding z-value becomes 10, which means 0, 2 lies on the isovalue line, which is z equals 3x1 plus 5x2 equals 10, okay? And rewriting this as x2 equals negative 3/5 x1 plus 2, right? Which means this line has a slope of negative 3/5 and the x2 intercept of 2, right? Okay, now let's go back to the computer screen. And all the isovalue lines have the same slope, right? So once we have drawn one isovalue line, we can find all other isovalue lines by moving parallel to the isovalue line we have drawn. And in this problem, the objective function g will increase if we move in a direction for which both x1 and x2 increase, right? So we construct another isovalue line, which is this. By moving to 3x1 plus 5x2 equals 20 in this direction, northeast direction, right? Likewise, the objective function g will increase if we move in this direction further, So we construct additional isovalue line, and we know the optimal value of 36 for this problem would be found with the isovalue line intersecting the feasible region, right? Okay, now then let's talk about the graphical explanation of sensitivity analysis. And first, let's suppose we'd like to know the effect of a change in an objective function coefficient, which means we'd like to know the effect of a change in the slope of the objective function. Okay? And here, let's say C1 is the contribution, the profit by each door. Okay? So it is the unit profit by each door. Now we will see for what values of C1 the current basis remains optimal. Currently, the C1 is 3, right? The C1 value is 3, right? And each isovalue line has the form, which is C1 x1 plus 5x2 equals constant, right? And this becomes x2 equals negative C1 over 5 x1 plus constant, right? And this isovalue line has a slope of negative C1 over 5. Is that correct? And suppose if we change the value of C1 so that the isovalue line becomes steeper than the plant number 3 constraint. The plant number 3 constraint is here. Okay? Then what happened to the optimal solution? Does the optimal solution remain the same, or does it change? It's going to be changes, right? Is that what you're saying, right? Then how much does it change? Okay, then let's see what happened. If a change in C1 causes the isovalue line to be steeper than this plant number 3 constraint. Okay? Just look at this. Now, the slope of isovalue line is steeper than the one in plant number 3 constraint, right? So in that case, does the optimal solution remains the same as before? Of course not, right? To find the optimal solution, we need to find the point, the feasible region, with the largest value of g, right? So we need to graph an isovalue line. But we already have one isovalue line, which is this, right? So what we need is to find all other isovalue line by moving parallel to the isovalue line we have. Okay? And in this case, the objective function g will be increased if we move to the northeast direction. Okay? Which is this direction. So we construct additional isovalue line, right? Now we know the new optimal point, which is the value of 22, is right here. Okay? Where the iso value line, again, intersecting the feasible region. Okay? So this is the new optimal point. So we may conclude that if a change in C1 causes the iso value line to be steeper than the plant number 3 constraint, then the optimal solution will change from the current optimal solution, which is point B, to a new optimal solution, which is point A. Is that right? And if the profit for each door is C1, the slope of each iso value line will be negative C1 over 5, right? Because the slope of plant number 3 constraint is negative 3 over 2, the iso value line will be steeper than plant number 3 constraint. If negative C1 over 5 is less than negative 3 over 2. Is that correct? This is the slope of constraint number 3, and this is the slope of iso value line. Okay? So I said the iso value line will be steeper than plant number 3 if this is satisfied, right? Which means C1 is greater than 15 over 2 from this. Okay? So in this case, the current basis will no longer be optimal. Okay? I said, in that case, the current basis will no longer be optimal. The new optimal point will be point A in our diagram, right? In this figure. Okay, and early today I said Lindo provides useful information for sensitivity analysis, right? Here in Lindo output, the objective coefficient ranges for each variable represents the amount by which the objective coefficient can be increased or decreased without causing a change in the current basis. So the allowable increase in the objective coefficient ranges So the allowable increase in the objective coefficient ranges is the amount by which the objective coefficient can be increased without causing a change in the basis, right? And currently, the C1 is 3, right? Here, the current coefficient value for x1 variable is 3, right? So if C1 becomes greater than this 3 plus 4.5, which is the allowable increase limit, I said if the coefficient of x1 which is C1, right? So if C1 becomes greater than 3, that is the current value, plus 4.5, that is the allowable increase limit, which becomes 7.5, right? That is 15/2. Then the current basis will no longer be optimal. And we were already known this fact, right? From here, right? Okay, then now let's see how to get the allowable decrease limit of 3 here. Okay? Suppose we change the value of C1 so that the isovalue line becomes flatter. Okay? And then it becomes steeper than the plant number 2 constraint. This is the plant number 2 constraint. Okay? Then what happened to the optimal solution? Do we still have the same optimal solution? No, right? Now let's see if the optimal solution remains the same as before or not. So by using the isovalue line, we may determine the optimal solution. And because we already have one isovalue line, which is this, what you need to do is to find all other isovalue line, right? And because the current optimal in the current objective function value z will be increased if we move in the northwest direction, which is this direction. We construct another isovalue line, right? And we know the new optimal point is right here. Okay? This is the point C is the new optimal solution, where the isovalue line intersecting our feasible region. Is that right? So we may say that if a change in C1 causes the isovalue line to be steeper in positive direction, then the plant number 2 constraint, which is this, then the optimal solution will change from the current optimal solution at point B to a new optimal solution at point C, right? And the slope of the plant number 2 constraint is 0, right? If the profit for each door is C1, again, the slope of each isovalue line will be negative C1 over 5. So, as we did before, if the slope of the isovalue line, which is C1 over 5, is greater than 0, this is the slope of isovalue line. 0, the slope of the blunt number 2 constraint, right? Number 2 constraint. If this relationship is, if this condition is satisfied, which means if C1 is less than 0, then the current basis is no longer be optimal. The point C becomes a new optimal point, right? Okay, then let's go back to the computer screen. And in Lindo output, again, the objective coefficient ranges indicate by this amount, the objective coefficient can be changed without causing a change in the basis, right? And according to the Lindo output, here the allowable decrease in the objective coefficient ranges for x1 variable is 3. Which means by this amount of 3, the objective coefficient can be decreased without causing a change in the basis. Okay? So currently, the C1 is 3, right? So if C1 becomes less than 3, that is the current value, minus 3. What is this? That is the allowable decrease limit. This becomes 0, right? If C1 becomes less than 0, then the current basis will no longer be optimal. And we've already known this too from up here, right? So let's go back to the computer screen. So in summary, we have shown that if all other parameters remain unchanged, the current basis remains optimal. Okay? For the C1 is greater than equal to 0, but less than equal to 7.5, right here. Okay? Which means within these ranges, the window glass should still manufacture how many? 2 doors and 6 windows, right? If you look at this, the window glass should manufacture 2 doors and 6 windows, right? Okay, let's go back to the computer screen. So I said within these ranges, the current basis remains the same, okay? So this range, actually these regions All these reasons defines the range in which the objective function coefficients can vary without changing the current optimal solution. Okay? And we have learned from the Lindo output the allowable ranges to stay optimal for C1 can be obtained from this, right? 3 minus 3, that is the lower limit, and 3 plus 4.5, that is the upper limit, right? So 3 minus 3 greater than equal to, and C1 less than equal to 3 plus 4.5. And this becomes C1 must be greater than equal to 0, but less than equal to 7.5. Okay? We've got this result already. Okay? Of course, even if the C1 is within these ranges, the window glass profit will change, right? For example, if C1 is 7, then the window glass profit, for example, if C1 is 7, then the window glass profit will be 7 times 2 plus 5 times 6, right? Which is 44 instead of 36, right? But the point is, we still have the same optimal basis, okay? Okay, then now let's find out the effect of a change in the right-hand side on the LP's optimal solution. Of course, if you change the right-hand side value of a constraint, the feasible reason may or may not change. And perhaps it causes a change in the optimal solution to the problem. And the graphical analysis can also be used to determine whether a change in the right-hand side of a constraint will make the current optimal solution infeasible. Okay? Here, let's say the B1. B1 is the number of available production time for plant number 1. Okay? Then currently the B1 value is 4, right? And now we will see for what value of C1, what value of B1, the current basis remain feasible. And the change in B1 shifts the plant number 1 constraint parallel to its current position. And the current optimal solution at point B is where the plant number 2 constraint and plant number 3 constraints are binding. Is that correct? At point B, plant number 2 and plant number 3 constraints are binding. Okay? And if we change the value of B1, then as long as the point where the plants number 2 and number 3 constraints are binding remains feasible, the optimal solution will still occur right here, where the plants number 2 and 3 constraints intersect. Okay? Is that complicated? Okay, let's see. If the value of B1 is decreased to 3, okay? Then we still have the same optimal solution at point B, where the constraint number, plant number 2 and plant number 3 constraints are binding. Is that right? If the value of B1 is decreased to 2, this value is 2, we still have the same optimal solution at point B. If the value of B1 is decreased to 1, what happened? Do we have the same optimal solution? No. Like this case, for B1 is less than 2, the plant number 2 and plant number 3 constraints are binding at an infeasible point. Is that right? So in this case, the current optimal solution, the current optimal point is no longer be feasible. Okay? And in Lindo output, the right-hand side ranges for each row are the amount by which the right-hand side can be changed, while the current optimal solution remains feasible. Okay? In other words, within these ranges, we still have the same set of binding constraints. Okay? So the allowable decrease in the right-hand side ranges for each row are the amount by which the right-hand side can be decreased without changing the current binding constraints. Okay? And currently, the B1 is 4 here, right? Here, the value 2 from the allowable decrease means the B1 value can be decreased by this amount without causing an infeasibility of the current optimal solution. Is that right? So if B1 becomes less than the 4 current value minus 2, the allowable decrease limit, which becomes 2, if B1 becomes less than 2, then the current optimal point becomes an infeasible point. Okay? Let me write it down for you. If B1 becomes less than 4, which is the current value, minus 2, that is the allowable decrease limit. If B1 becomes less than 2, then the current optimal point becomes an infeasible point. Okay? Now let's see why we have here infinity as the allowable increase limit for B1. Okay? So currently the value of B1 is 4 right here. Okay? And if we increase the value of B1 to 5, of course, the feasible region has been bigger. However, it doesn't impact on our optimal solution, right? Our optimal solution is still in the feasible region, right? So we still have the same optimal solution at point B, where the plants number 2 and number 3 constraints are binding. Is that right? If the value of B1 is increased to 6, we still have the same optimal solution at point B. If B1 becomes 7, of course, nothing's changed at all, right? So, what can you say from this result? Increasing the value of B1 doesn't affect on the current optimal solution, right? We still have the same optimal solution at point B, where the plants number 2 and number 3 constraints are binding. Okay? And in Lindo output, the allowable increase the right-hand side ranges for each row are the amount by which the right-hand side can be increased without causing any changes in the binding constraints. Or within these ranges, the current optimal solution remains feasible. Of course, assuming no changes occur in the other right-hand side values. Okay? And we've known that the increasing the value of B1 doesn't affect on the current optimal solution. So we have infinity as the allowable increase limit of B1, okay? Over which the current optimal solution remains feasible and the current set of binding constraints remains the same as before, okay? Okay, then, how about the effect of changes in the right-hand side in the last constraint? Let's say the B3 is the number of available production time for plant number 3. Then the value of B3 is 18, right? Now let's see, for what values of B3 the current basis remain feasible. If B3 is decreased to 10, for example, what happened? The plant number 2 and number 3 constraints are binding at an infeasible point, having x1 is less than 0. Or before that, okay. That's the case. Okay. Okay, what about this case? Currently B3 is 18, but if B3 is decreased to, what value is that? It should be 14, okay? Right now, the B3 is 14, okay? Then the plant number 2 and number 3 constraints are binding in the feasible region, okay? If B3 is decreased to 12, then the plant number 3 and number 2 constraints are still binding in this feasible region, okay? But the B3 is decreased to 10, in this case, the plant number 2 and number 3 constraints are binding at an infeasible point, because in that case, x1 value is less than 0. Is that right? And the current basis will no longer be optimal. So the allowable decrease limit to stay feasible for B3 would be B3 should be greater than equal to 12. Okay? How about the allowable increase limit to stay feasible for B3? The 24? Okay, let's see. Okay, currently the B3 is 18. If B3 is increased to 21, for example, what happened? The plant number 2 and number 3 constraints are still binding in the feasible region, right? If B3 is increased to 24, what happened? Again, the plant number 2 and number 3 constraints are still binding in the feasible region. However, if B3 is decreased to 27, increased to 27, then the plant number 2 and number 3 constraints are binding at an infeasible point, because the plant number 1 constraint for door is not satisfied, right? That is the plant number 1 constraint. And the current basis will no longer be optimal. So the allowable increase limit to stay feasible for B3 would be less than equal to 24. Okay? And in window output, the right-hand side ranges for each row are the amount by which the right-hand side can be increased or decreased, right? While the current optimal solution remains feasible. And let's go back to the computer screen. And currently, the B3 is 18, right? And the allowable increase limit is 6, which means P3 must be less than equal to the current value 18 plus 6, which is 24, right? So P3 must be less than equal to 24, and the allowable decrease limit is 6, which means P3 should be greater than equal to 18, the current value, minus this value, 6, which is 12, right? So the allowable range to stay feasible for B3 is greater than equal to 12, but less than equal to 24. Does that make sense? Okay, this is all for today. And next time, I'm going to continue to talk about the sensitivity analysis. And probably I will going to give you some example problem, which I hope to help you to understand the sensitivity analysis. Okay? Okay, thank you. I will see you next time. Bye.